Now, rather than just let you look at this one, and certainly by all means pause it and read it, I will tell you that there's very little about this comic that I get. A lot of stuff I'm just not familiar with. But I love the middle slide right here. This just seems like something very clever that one of you fine, nerdy, geeky people that are sitting at home right now watching a calculus video might come up with at some point or another. But again, if you're not done reading it, pause it. Otherwise, here we go. Today we're going to look at another application of integrals, 7/4 lengths of curves. Now, if I were to just draw a straight line on the board, perhaps on a grid, and say find the distance, well, you would go to your distance formula. Square root of x2 minus x1 squared plus y2 minus y1 squared. But what happens when that straight line becomes a curve? Well, suddenly our distance formula is no longer valid. It's only for straight lines. So we're going to look at that today. Specifically, we're going to look at finding the distance of a sine wave, a smooth curve, and then we're going to look at some special cases and what happens when we have vertical tangents, corners, and cusps. And here we go. Now imagine a nice smooth curve like this blue line right here. If I wanted to come up with the distance of that, just using good old pre-cal algebra 1 stuff, I could break up that line into subsections, like there to there, here to here, there to there, and so on, and use my distance formula. Now, x2 minus x1 squared, we could just write like delta x squared and delta y squared for the y's, and come up with that measurement there using the distance formula, and then add all of those up. Well, just like we've done with the area, we ask ourselves, how do we make it more accurate? Well, if we make the subsections smaller and use more of them, then there's less error, and that makes it more accurate. And if we just kept going and use infinitely many with basically no distance in between them, then that's how we get the exact answer. And so this is the basis of our formula up here. Now, you may be wondering how we go from there to there, so I'm going to show you just something real quick, real neat. If we take this formula here and we rewrite it like this, instead of delta x like that, delta x we could also write dx squared, and instead of delta y, dy squared like that. Now, if I were to divide out everything by a dx on the inside, so if I divided everything by dx squared on the inside, that would give me dx divided by dx is 1, and this part right here would be dy over dx, still all squared. And since I divided on the inside, I would multiply on the outside. But also on the outside, when you take something out of a square root, you of course take the square root of it. So I'm multiplying out here by the square root of dx squared, which is just dx. And you see, that's what we have right there. Now, instead of going from a to b on the x, we can go from c to d on the y. And we do that, but notice it's dx dy, so this one, everything's in terms of y on this one, everything's in terms of x on this one. Most times this top one is better, on some occasions the bottom one is better, and I'll tell you about those as we go. So we begin. We're going to find the length of the sine curve from 0 to 2 pi. So imagine taking, if you will, a ruler, laying the tip of the ruler down here, and you're bending it along, and you're following the curve, and then coming to the end, and how long is that curve? Well, we start with this. 1 plus, now where did I get the cosine squared x here? Well, remember that this part right here is the derivative squared. What's the derivative of sine x? Well, cosine x. And then we square it, cosine squared x, from 0 to pi. You erase this because it's going to get in the way of the rest of the things that we do. And use our calculators to come up with that answer. So 7.64 units. If each of these is an inch, then this would be 7.64 inches. It's that simple. Find the derivative, square it, add 1, and then use your calculator to come up with the integral. Right, find the exact length of the curve below from 0 to 1. Here's our curve right here. Now again, this one looks nasty. This looks very, very nasty. But you'll notice as we go that it actually does simplify quite a bit. So let's start by finding the derivative. So we'll take the 3/2 out front. The 3's cancel. 2 goes into 4 2 times. And then we subtract 1. So instead of 3/2, it goes down to 1/2. And the derivative of -1 is nothing. Now we take that derivative and we square it. Well, 2 radical 2 squared is 8. X to the 1/2 squared is just x. So all of that goes down to 8x. 1 plus the derivative squared would be 1 plus 8x from 0 to 1. And we're going to do some u substitution here to solve this problem. If u is equal to 1 plus 8x right here, u equals 1 plus 8x, then du would be 8 dx. For those of you that have forgotten u substitution, that's why I'm showing you. So I need an 8 dx. I multiply by 8 there, 1/8 on the outside there. And then I can make my substitution. That becomes u to the 1/2 du. And remember, we also change these. Plug in 1, 1 plus 8 is 9. Plug in 0, 1 plus 0 is 1. The antiderivative of u to the 1/2 is 2/3 u to the 3/2. Don't forget we have the 1/8 out there still. And we can take that 2/3 and the 1/8 and make it 1/12. And plug in our 9 and our 1. 9 to the 3/2 minus 1 to the 3/2. It comes out to be 27 minus 1, which is 26 over 12, which reduces to be 13 over 6. So 13 over 6 units. Now, this one gives us a problem. If we were to try and work this problem out from -8 to 8 of x to the 1/3, the derivative of x to the 1/3 would be 1/3 x to the -2/3, or 1 over 3x to the 2/3. Even when we square that, squaring it would be 1/9 x to the 4/3. The problem is going to be is that at 0, if I were to plug in 0 right here, you see we have 0 on the bottom. You have an infinite situation, not going to work. So we can change up the problem by doing the inverse. This is a sketch of the inverse of this over the same distance. -8 to -2 becomes -2, -8. 8, 2 goes to 2, 8, and then we sketch our inverse. Remember, inverse is where x is the mod switch places, and the distance is the same. If you sketch an inverse function over the same interval, just flip-flop by the x and y, it gives you the same distance. Well, if we're going to do the inverse, we need to come up with the inverse of this up here, which basically means we need to solve for x in terms of y. And we do that. When we do that, we cube both sides, x equals y cubed. Now take the derivative, square it, add 1. That would be 3y cubed, I'm sorry, 3y squared. 3y squared would be 9y to the 4th. And notice instead of going from -8 to 8, we're going -2 to 2 right here. Plug that into your calculator. Don't try and work that one out by hand. 17.26 units long. My apologies for coughing on the video. What about when we have a corner point or a cusp? Our job is to find the length, and yet again, for the same reason that we had on the last one, we couldn't just work it like this, because when we come to this part here with the derivative, it's going to be undefined. So here is what we would have to do. Now, I will tell you, and certainly I would not have expected you to get this, but you could have, I guess, had you been real careful, come up with various points from this function. You know, x equals 0, find y, x equals -1, find y, x equals -2, find y. And from those points, you could have extrapolated these two formulas. But I'll just go ahead and give that to you now. I won't force you to do that right now. But you see here we have this parabola that's to the left, represented by x squared plus 3x. We have this parabola here on the right, represented by x squared minus 5x, and we're going -4 to 4. This is how we get around a corner point. We break it up into subsections, and we find the integral of each subsection. So, for instance, I'm going to go -4 to 0 of this function, 1 plus, now the derivative here would be 2x plus 3 squared, plus, and then we go 0 to 4 for 1 plus, and then 2x minus 5 would be this derivative squared. and then plug that again into your calculator. Calculators are wonderful things, aren't they? 19.56 units long. But again, the hard part in this one is coming up with this function right here. At some point or another, if you want to come in, I'll show you how to do it. Again, it takes any 3 points on a parabola, can come up with the formula of the parabola using ax squared plus bx plus c.
Hannah Lawrence.
Well, again, tons and tons of announcements this morning, ladies and gentlemen. You just have no idea. Be thankful you're not here. The last thing we're going to talk about actually is not in your book. I don't know why it's not in your book, because it still is a topic mentioned from time to time on the AP exam, but it's the idea of surface area. Now, the reason I'm throwing surface area into this section is because it's so much like arc length. I mean, look here. If you look at the formula for surface area, this radical 1 plus f prime of x squared dx, that's the exact formula for the arc length, or for the length of a curve. But it throws in this radius function here, and we'll talk about that, what that is here as we go. And then a 2 pi. Now, basically what this is, it's the formula for the volume of a cylinder. But again, you'll see that as, I'm sorry, not volume, but surface area of a cylinder. And you'll see that as we go. So let's go ahead and jump into a problem. We're going to find the area of a surface by taking x cubed and from 0 to 1 and revolving it about the x-axis. So we are going to have a three-dimensional object, just like we did volume yesterday. But instead of coming up with the inside volume, we're just going to do the surface area on the outside. So again, it's like that lateral surface area, and we're taking that lateral surface area and we're revolving it around. So first of all, as we did with arc length, we're going to find the derivative of the function. Derivative of x cubed is 3x squared. We then square that derivative, 9x to the 4th, and then you of course add 1, and that's what goes inside the integral right there. Now, this part right here, again, represents the radius. I'm not going to draw a sketch here because I don't really have room. But 99 times out of 100, this radius is just simply the function itself. Now, if you want to come to class tomorrow, I'll show you what I'm talking about. But that radius function is usually just the original function itself. And we now have this, and now it's just a matter of solving. Certainly feel free to work this one out on your calculator. It is a U substitution problem if we want to do that. Using U substitution, we would come up with this formula. If you want to know what I did there, I went U is 1 plus 9x to the 4th, and du is 36x cubed. Well, I need a 36 on this x cubed, which means out here I need an over 36. Well, 2 pi over 36, that's the pi over 18. So this on the inside becomes u to the 1/2, which you know becomes 2/3 u to the 3/2 when we do the antiderivative. And then we resubstitute back in the 1 plus 9x to the 4th. I'd show you this, even though we don't usually do it that way, just to show you that it can be done that way. You know, most times we don't resubstitute. We just change the limits of integration. But you can resubstitute if you choose to. Now we plug in our 1, plug in our 0, and we end up with this. Took the 2/3 out here with the pi over 18, made it pi over 27. And we end up with that answer right there, which is what your calculator would have given you all the way back here at step 4 if you had chosen to do that. Now, one of my favorite problems to work is a yo-yo problem. A yo-yo is made from a sphere by removing a slice from its center. And suppose a yo-yo is cut from a sphere, radius 3 centimeters, in such a way that its width is now 4 centimeters. With the slit 1/4 centimeter wide in its middle, find the surface area of the outer portion of the yo-yo. Now, I really wish that I had a picture to go with this. I used to, and I don't have it anymore. But the shape is defined by this function right here. And we're going to go from 1/8 to 2. Now, how did I get the 1/8 to 2? Well, it's width of 4, so half of 4 is 2. And I took a quarter out of the middle. Well, half of a quarter is an eighth on each side. Now, see, now our video is almost done, so We're going to make about a 1 to 2 minute video to finish this up in just a moment.